let's continue part B, the item B, Intrinsic Geometry, Exterior Algebra in 3 dimensions. Now, part 1, we are talking about manifold. But as I said, a main tool for the intrinsic geometry is the exterior algebra. Here in this lecture, I will introduce the exterior algebra, but knowing that we'll talk in detail the subject in some videos ahead. Okay? So let's introduce to the exterior algebra. Now I will start. Okay, let phi the function of the coordinate c1, c2, and c3. From calculus, the differential of phi is equal partial of phi with respect to ci dxi. Okay, that's the I here is equal 1, 2, 3 is dummy index. Okay, now, okay, you see these are, I will draw C1, C2, and C3. You see, there is no position vector. Attention now, no position vector. Okay, as I insist, okay, to say that in intrinsic geometry there is no position vector. Later you see how you will obtain a point. Okay? So now since Ci, I is equal 1, 2, 3 are independent coordinates, you see clearly partial derivative of xi with respect to xj is equal delta ij. Now, when I is equal to j, okay, this is will be 1. When I is different from j, this will be 0, since they are independent coordinates. Now, substitute phi by, let's say, cj. Okay? Substitute here, over here. So d cj is equal partial of cj with respect to ci d ci. You see, I'm just substitute phi by cj. So this is equal delta ij dxi. Do you remember the property of the conic delta? So this exactly dxj. So I consequently we define the inner product like this. This is a dxi. That's right here. Doesn't matter, okay, because the partial derivative xi dxj is equal delta ij. Since you see here, okay, that when ci is equal cj, this will be 1. Then you reproduce, in this case, dxj. Okay? So we define this inner product. Now, what's very, very important, see, you see this later, you see basis vector partial ci. Okay, now you see when you talk about manifolds, you see that this here, this belongs to this case, okay, to the tangent vector space. And basis vectors, okay, dxi belongs, attention now, okay, to the cotangent vector space. Okay, then you say, what do you mean by tangent vector space and cotangent vector space? This will be clear when we initiate talk about manifolds. Okay, so keep this in your mind that you come later to this definition over here. So we now, that's a very, very interesting. We make an analogy. This, okay, I will erase here, okay, that I have more space over here. See? You see that it's a very, very interesting analogy between exterior geometry and intrinsic geometry. See? I'll see this analogy. Now, I'll erase it here. Erase. So look how interesting. You see, attention now, part A, go over there, okay, I have two, parts 1, 2, 3, 4, 5, 6, and 7, okay, when you talk about exterior geometry, okay, part B is intrinsic geometry. Then the analogy, I'll repeat here, the analogy. Here I have, in this case, extrinsic geometry. And this I'll have intrinsic geometry. Now, attention now, part the A, okay, the A item, this is a B, okay, then we saw like this. This is my vector space. I'll write here, vector space. And this one is a dual vector space or covector space. Look how interesting. Okay, this I have the basis, let's say AI. The components Ci and the coordinates ci and the components of the vector v is vi. Attention now, this is covariant basis, this is contravariant coordinate, and this is contravariant components of a certain vector v. Okay, this is AI, this is AI, VI. These are the bases, okay, belong to the dual vector space. This is a coordinates belong to the dual, and this is the components of a vector. We did this a lot, okay? Now, what is important is this. Still in the analogy here, we have AI dot AJ is equal delta IJ. See, also AI dot AJ is GIJ, and AI dot AJ is equal GIJ. You see, this is called dot product. Now we move this from the intrinsic geometry, okay, that there is no, attention now, there is no position vector, okay? So the analogy is as follows. This I'll have, we'll call this the tangent space.